Hey, good morning, everyone. Um, let's see. Today's video will be the first video in about photolithography. Um, if you're keeping up with the syllabus, you may have noticed that I've fallen a day or two behind. Um, and I'll try to catch up before the end of the quarter. I don't think it'll be a problem. I think actually I had allotted 3 lectures for photolithography, but I would anticipate probably covering it in 2. So that would be today and tomorrow. That will pick up a day. And then we'll just pick up a day maybe later when we talk about nanomaterials. I could easily condense the properties and the manufacturing into one lecture. Anyway, today homework 5 is due. I just posted a new set. That'll be the last homework set. Homework 6, that has problems through chemical vapor deposition. The material after that will be covered more qualitatively. That provides time for you to work homework problems on material that we've covered. And then also, so homework 6 will be the last homework set, and there's one more assignment after that, is the case study. I will be posting soon some more details on the expectations for that, and how I would like to execute that. But basically, it'll be you all giving a short presentation on the development of a class of materials, kind of a historical case study. Okay, so I think that covers the announcements. Like I said, today is lecture number 1 for photolithography. I put the notes up as one solid lithography block. So it's 7 through 9 all in one, chapter 7 through 9, all in one. So the sharing doesn't seem to be working quite right. There we go. Okay. So lithography notes are all in one block. And the way that the lectures I anticipate will break down is that this lecture will be about the light side of lithography. That'll make more sense as we go. And then the next lecture will be about the photoresist and non-optical lithography techniques. I should also mention that this is probably the one area where the age of the text is probably most evident, right? This is where a lot of the innovation is focused in microfabrication. And so what we're covering here, what I'm covering, is not meant to be a up-to-date, state-of-the-art lesson. Instead, I'm more focused on the general principles and concepts, and also what the limitations are. So as new innovations are coming online, they are focused on overcoming certain challenges. And those are what, that's part of what I'm going to be focusing on, is sort of the basic physics and science involved with how the process works and how you improve it, not necessarily what the most up-to-date feature size is or the details of the most state-of-the-art technique. Right, this is kind of meant to be an introduction for material scientists. Those of you in the EE department, this is not the first time you've seen this stuff, and so you may have other classes that went more in depth into more state-of-the-art techniques. So kind of where this fits in. So we have talked about right, crystal growth, and then we talked about I'm blanking here. Yes, oxidation, ion implantation, rapid thermal processing. So we have covered, some of the processes that will be done to the wafer on a global scale, meaning you expose the whole surface simultaneously. But you don't make a device by oxidizing the silicon wafer, right? Or I guess you can make one big device out of the whole wafer, perhaps. What you're doing is you're making many devices. So, but to define the regions, right, to encode that information of where certain regions will be oxidized or doped with impurities, right, you need to cover up the areas that you don't want to be exposed, right, and expose the areas where you do. And so photolithography is the process of encoding that information in the surface. And it's also, so it's, that's where the information is. And the state of advancement of the lithography process dictates the size of the devices that you're building on the surface, and thus their density. And so the more transistors or memory elements, or whatever it is you're making, that you can pack into a certain area, right? The more calculations you can do, the closer the devices will be to each other, all of which increases the processing speed and the power of the device or the chip that you're ultimately making. And so we talked about on the very first day of Moore's Law, you guys are probably all familiar with that, that describes kind of the exponential growth or the exponential reduction in individual feature size, and thus the growth of the density is, you get a doubling every 18 months or every 2 years or whatever of the density. And so achieving those gains has been almost solely the result of advancements in photolithography, right? So as you get better lithography, you can decrease the minimum feature size and pack more of them in there and have a faster chip. And so we're focusing on lithography. Within lithography, right, improving and reducing the size almost always means that you're reducing the wavelength of light that you're using in your lithographic process. And so there's pressure to push the wavelength into lower and lower and lower wavelengths so that you go deeper and deeper into the ultraviolet, eventually transitioning into other parts of the spectrum, such as soft X-rays or high energy electrons. As we'll see later on in this lecture, it's the wavelength that dictates the ability to reproduce a certain pattern on the surface. And that's just due to the wave nature of the light. However, as you push those wavelengths lower and lower and lower, the cost increases because you have to redesign the whole process around that wavelength, right? So as I go from, UV to deep UV to soft X-rays to X-rays, as I'm pushing lower and lower wavelengths, right? The optical properties of my my optical elements, if I have, lenses or in my optical train, as I'm moving the light to the surface, the optical properties of all of those elements are wavelength dependent. And so as I go to smaller wavelengths, I could have higher absorption and less transmission at that wavelength. And also the photoresist, which we'll talk about in more depth in the next lecture, that's also wavelength dependent. So the light is coming in and changing that photoresist chemical in some certain way, and that the interaction that reaction that's happening is wavelength dependent also. So you may gain a smaller feature size with a smaller wavelength, but you might have to redesign your entire process, which is expensive. And so as they go smaller and smaller and smaller, it's kind of a scenario of diminishing returns where, to get that next doubling, you may have to put in 4 times as much R&D, right? And the double after that might be, 8 times as much R&D. And so that's why you hear talk about, what's beyond silicon, because eventually we're going to exhaust all of the tricks that are done to reduce the size, and you're going to be at a limit, right? And we see this a little bit where, for in the 90s and early 2000s and so on, you were seeing the speed of an individual processing chip increase dramatically, right? But now, you don't see an individual processor with much more than, say, 3 or 4 gigahertz. Now, if you want to have a faster computer, right, they're putting in multiple cores, right? And so we're having to parallelize because we can no longer, or it's becoming more difficult to make a single chip with more transistors. We've kind of reached the limit of some of these things, and right, this also spurs research into other ways of computing, right? So quantum computing, I've not heard of that, is increasing, and they're trying to figure out, okay, how do you make qubits, which are the little kind of a quantum transistor. How do you program in a quantum computer, right? So they're saying, okay, we've reached the limit of silicon. What's next? Anyway, okay. But here we're focusing on the basics, not exactly the state of the art, as I said. And so the basics of lithography, what we're trying to achieve here, is to create a pattern, right, on the surface of your wafer by exposing a layer of photosensitive polymer, right? That's what we call the photoresist on the surface, to a pattern of light that is created by shining an optical source, generally ultraviolet or smaller wavelengths, through a mask. Right? So you have a mask that has opaque and transmissive regions, and so the light shines through some and not others and creates the pattern on the photoresist. Right? That photoresist is chemically changed, and so that either the exposed or the unexposed, depending on which photoresist you're using, is then removed, leaving the pattern that existed in the mask on the surface. Right? Then you can dope or etch or oxidize the exposed silicon and not that is covered by the photoresist. Okay. And so this basic process has a couple of steps, right? The first step is to get the light from the source to the surface. And you can measure the quality of this process 3 ways. The first is resolution, right? This would be, right, how small of a feature size can you reproduce on the surface, right? The second is called registration. Registration has to do with the fact that you can't make a device from one mask, right? First you need to define, certain regions. You may have layers on top of one another. You may have to start, say, build the N-type, then the P-type material, or add a contact, or, add another layer of silicon, right? So, you're building up these devices from the substrate upward, but it's, it could require 15, 20 different masks. And so registration relates to the ability to precisely line up one mask over top of another mask. And this is done with specialized alignment marks on the masks, and so you need to be able to register your masks better than the resolution, right? You'd say, maybe a rule of thumb would be less than 1/3 the resolution, right? So you would say if you had a minimum feature size, right, that it would vary at the edges less than 1/3, right? You probably want to have quite a bit better than that. But to kind of visualize this, and this is an analogy given by Campbell towards the end of the lithography chapter, you can think about registration and sort of the high demands of this kind of work. It's analogous to building a skyscraper, right? So you got 100 floors or something, and you're building them one floor at a time. And skyscrapers require utilities, right? So you've got pipes running up and down the building, carrying water and waste and air and wires that run between them. And so building with microfabrication techniques is analogous to building a skyscraper one floor at a time, right? So you build the entire floor from the beginning to end, and then with furnishings and everything, and before you build the next layer. And so if you want to have these wires and pipes running between each of them, right? So in microfabrication, right, there are all sorts of connections between the different layers, right? So this would be analogous to building a skyscraper with 100 million pipes and wires running between each floor, and to get them to line up, right, they might be, say, 2 millimeters in diameter or something, right? You're talking about, a normal electrical wire that you would run in the house or something. You would need to line up each of those connections, right, to within 0.05 millimeters. And so you can see here with this analogy, right, the importance of being able to line up one mask to another, right? If your registration is not good enough, then you may as well not even try to make your device. And so not only do you need to be worried about alignment of the various marks on the various masks, but you need to be cognizant of the temperature of each of those, right? So each of these masks is going to be made of fused silicon with deposited chrome, and so fused silica has a coefficient of thermal expansion, right? So as you increase the temperature, it expands slightly, and so in microfabrication, we're working at such a small size, right? Is that even a minimal thermal expansion is going to move those elements on the mask enough to change the overlap, right, of one mask to the next. And so you want to have uniform thermal expansion, and you also are going to need to keep the masks at the same temperature, right, so that they are to the same degree of thermal expansion, and they line up. Okay, so that was the first two. The third is throughput, right? This is simpler. This is essentially just production speed, right? How many wafers can you run through your photolithography process in a given time? And this is kind of this is an economic factor in the sense that, right, if you can make 100 at a time, right, then your cost just went down by 100 times. And all of these measures here, resolution, registration, throughput, right, everything in this business is statistical in nature. And so if you were to measure, the registration is such and such, plus or minus some value, right, we're talking about bounds that are specified to within 6 standard deviations, right? If you've ever heard, Lean Six Sigma, that sort of thing, right? That's the Six Sigma that we're talking about. And so this is sort of like a 99.999% accuracy with Six Sigma. Okay, so this first part of the photolithography is about the light, right? How do we get the light from the source to the surface? Um, Next video we'll talk about what happens after that. Um, and so this is an optical process, or at least a light-based process. And anytime you're dealing with light, um, you can think about it. It's got this dual character, where most of the time it's helpful to think about it as a wave, and then some of the time it's helpful to think about it as a particle, right? Um, Subatomic particles have the same characteristic, where sometimes, most of the time, but it's inverted in the sense that most of the time you think about an electron as a particle, but it also has a wavelength, which we call the Broglie wavelength. But light is most often thought of as a wave. And when you're tracing a light ray, say through a telescope or microscope or some sort of macroscopic optical system, we think about light as traveling in a ray, right? Where it travels from one point to the next and in straight lines, unless it's reflected or refracted by some sort of optical element, in which case it travels in a new direction in a straight line. And that's okay. You can think about that. It's sort of the ray tracing model. That's fine if you're in a regime where the objects that the light is interacting with are much, much larger than the wavelength of the light. However, right, in microfabrication, we're talking about small things, right? And we want to make them as small as possible. And so we quickly run into the regime where the wavelength of the light is not much, much smaller than the objects it's interacting with, right? It's looking at a gap, say, in the mask that is on the order of the wavelength of the light. And then in that regime, what happens is that the ray tracing model breaks down because the wave nature of the light inserts itself and becomes one of the dominant factors. And so when light is interacting with objects or openings that are similar in size to the wavelength, we have to consider the wave nature of light and thus diffraction and interference, right? So diffraction, I think of as sort of bending around small features, and interference is when you have two different waves that are interacting with one another and either adding constructively or adding destructively, and that leads to maximum and minimum. And so in this regime, we can think about the opening here as being a secondary source, and a sort of a line of equivalent point sources here. And similar to dropping a pebble in a pond, each of these sources is going to give off spherical wavefronts, right? You can think about the atoms here in this fused silica, transparent region of the mask as being excited to vibrate, right? So the electrons are vibrating at the frequency of the incoming electromagnetic wave, and then it's re-radiating that energy in all directions, and so are all of the atoms, right, in this material here. And so we have these. This is first suggested by Huygens, I think in the 1600s or something. And so this is the Huygens, called the Huygens principle. And we have this collection of spherical wavefront emitters, right? And so our incoming light is being transferred into this this form. And so as the light propagates out from these these point sources in these spherical wavefronts, at some distance, right, all of these spherical wavefronts are going to interfere with one another to yield a pattern of maximum and minimum. And we get something maybe that looks like this, right, where we would have a square opening that would image, you would think, as a square. However, there is a more complex pattern of interference between these spherical wavefronts, right? So, at this point, they are constructively interfering, right, to the maximum extent, and right here they would be destructively interfering to the maximum extent. But then, in between, right, there is this natural variation, and also, right, you don't get instantaneous turn on and turn off. However, as you shift the size of this opening, right, so if I were to take this opening and increase it, then at any particular point, I would have more of these spherical emitters overlapping. And so that has the effect of dampening out this vibration, making this transition sharper, and what I recover is the square opening that I see here, right? As I go the other way, where as the opening gets smaller, right, or the wavelength gets larger, then the distortion becomes more apparent because I have fewer emitters that are adding constructively. And so I see more variation as fewer emitters are interfering with each other. I get the same effect also with a constant size opening of decreasing the wavelength, right? So that's one of the reasons why the lithography business is pushing always to smaller and smaller wavelengths, is because it shifts this pattern to be more representative of the opening in the mask. Okay. And so and then there's two kinds of interference, and the difference between them is just the distance from the source to the focal point, I guess. If you're close up, right, then you get a pattern that looks like this. It's called Fresnel diffraction. If you're far away, which we won't focus on here because generally in photolithography we're going to be close, far away is called Fraunhofer diffraction, and that's what you see if you remember from physics, doing like the two pinhole experiment or the double slit experiment, where you're far away and you see a sharp minimum or a sharp central spot and then fringes moving out from that, right? That's Fraunhofer diffraction. And this is kind of simplified in the fact that, okay, we're just talking about light interaction, light interference. In real systems, right, you don't just have one wavelength only, right? You could have multiple wavelengths. Your peak has some bandwidth. You're also imaging through optical systems, so you've got distortion and aberration in your lenses. You have a reflection at the interface between one index and another. So that would be within your mask, and also the photoresist at the surface, right? So just this pure interaction between the diffracting photons is just the start of your worries, right? You have other complexities due to how the light is getting from your source to your sample or to your wafer. And when we're performing microfabrication, right, we don't just have an isolated opening, right? We'll have an opening here, one here, one here, one here, right? If I'm trying to make thousands or millions or billions of the same device, then I'm going to have many, many, many of these features in very close proximity. So what we're not looking at an isolated opening, we're looking more at a repeated opening, similar to a diffraction grating, right? So a diffraction grating is many, many lines that are spaced very close together, right? The size and the spacing of the lines dictates the wavelength of light that it will interfere with. And what we see here is that when you have many, many openings very close to one another, the intensity in between never goes to zero. So if I look at an isolated one, right, the intensity out here eventually goes to zero. But if I have another opening here, right, I could actually have the same pattern just overlapping, right? So you can picture if I had an opening to the right here, it might produce this same pattern, but shifted to the right a little bit, right? And if these legs overlapped, and then I had another pattern here, so to speak, right here where the overlap is, the intensity would never fall to 0. And that's kind of what we have here, right? Where we have this intensity pattern due to very closely spaced features. And this difference between the maximum value at the opening, say, in the mask, and the minimum value in between is what is called the modulation transfer function, right, or the MTF, right? And that's just defined as the maximum difference divided by the sum of the max and the min. And that's just a way of measuring the contrast, right? So if I have a big difference, right, then I've got a big contrast between the maximum and the minimum, right? It's easy to tell where the maximum and the minimum are. However, as I decrease the feature size, the modulation transfer function also decreases, right? You can imagine, I wish I had a whiteboard function here, but I'll just try to draw it out with my cursor, right? I mentioned that there's a space over here. Well, if I make this opaque region smaller, that's bringing the spaces closer together, which means that I'm going to overlap these legs closer together, right? Which means that the difference in between, right, the difference between, well, if I overlap higher, right, then the minimum gets higher, right? So there's a smaller difference, a smaller contrast between the maximum and the minimum, and thus a decrease in the modulation transfer function. And this is important because the photoresist, as we'll talk about later, well, I guess it's talked about here, requires a certain contrast between bright and dim, right? What I want is, the light is creating some sort of chemical reaction, right? That changes the photoresist and makes it either more or less soluble so that I can remove either the exposed or the unexposed to leave the pattern. And that chemical reaction requires a certain amount of light to complete. And so you can see here this D sub CR, this would be like sort of the critical dose of light that is required, right? So it means that once I reach that critical dose, ideally, it would change, and so the pattern that I would leave behind would be, right, I would have solid photoresist in this region where I did reach this critical dose, and then I would lose everything else in between where I didn't reach that, right? The ideal case is not achieved with real photoresist, right? Real photoresist has this region where I have partial dissolution afterwards. And so as the modulation transfer function decreases, right, this region here becomes larger, and it limits how sharply I can define the edges of my features, and which degrades the pattern that I will produce. Okay, so where does the light come from? This is probably one of the areas where the state of the art is changing most rapidly, right? And what we'll cover here is perhaps a bit dated, but illustrates the progression from one source to another as we are chasing after smaller and smaller wavelengths. So at the beginning, and the most popular for a long time, was using high pressure arc lamps. So you have two electrodes, and you strike an arc between them, which creates a plasma. Now, in that plasma, you've got very fast, hot electrons, and so they are acting like a black body. So they're very hot, say 40,000 Kelvin or something. So they're emitting in the deep, deep UV. However, that's absorbed by the glass. Inside of this arc lamp, you also have atomic mercury, and which gets excited by the plasma, and you have the valence electrons of mercury excited to higher energy states. They then relax back down and give off the energy difference as an infrared photon, right? Depending on the wavelength, right, give them different names. You have what's called the G line or the I line, right? Those are just some of the more intense emissions from mercury that occur in the ultraviolet. You can also generate photons, UV photons, that are smaller wavelength, right? Higher energy, smaller wavelength, more useful for smaller features with an excimer laser. So in an excimer, so excimer is short for excited dimer, right? So dimer means I have two atoms and they're in an excited state. When they subsequently react, you get a de-excited state and the emission of a photon. That photon is in the ultraviolet, right, at a lower wavelength than you get from the G or the I line, and we can use that to reduce your feature size. However, as you transition, as I said, to the lower wavelengths, you have additional problems in that the transmission of your optics and your masks changes, and you become more absorptive to these deeper UV photons, which will decrease their lifetime. All right, so you generate the light with, say, an excimer laser or an arc pressure, an arc lamp, and then what do you do with it? Well, you have to get it to your mask. And so a typical system might look something like this, where you have your arc lamp and then collectors that collect as much of that emitted light. Remember that the light is emitted in all directions, so I have a parabolic reflector to capture that light, and then, say, a collimating lens, a fisheye lens to create greater uniformity, and then on various mirrors and lenses to eventually collect and focus the light collimated and uniform across the surface of my wafer. Or at least to the mask. So once the light gets to the mask, where does it go from there, right? And how is the mask positioned in regards to the wafer? Well, there's a couple of options, right? One is you could take the mask and the wafer and put them right next to each other, make them touching, right? This is what we do in contact printing. This is a simple arrangement, and it also is the one that decreases the diffraction the most, right? You can imagine, if I go back up to this diffraction picture, if I have my wafer right here, right, there's little time or space for these spherical wavelets to interfere with each other. The further they travel, right, the more you can get interference from wavelets that are spread apart across your image. And so if you have contact printing, right, you've pressed up your wafer right up against your mask, that diminishes the diffraction. However, that contact greatly increases your chances of creating defects. And the defects will produce, say, dirt or points of contact between will produce a defect, right? So you'll have an area that is not what you intended. So to reduce the defects, you want to put a little bit of space in between your mask and your wafer, right? This is what's done in proximity printing, where I have a 1-to-1 size ratio between the mask and the wafer. However, I create a small gap. Now that gap is ideally, very small. This figure here, figure 7.16 from Campbell, illustrates the distortion you get as you increase that gap between the mask and the surface of the photoresist, right? So at 0, at A, that would be 0, right? I ostensibly get perfect transfer, right? This would be the contact printing case. However, I could anticipate having higher defect densities. As I increase, right, say in steps of, I don't know, this is probably a few microns, I start to see the distortion. So my transition broadens. I see distortion along the maximum of through the center of the feature. And as I go to greater and greater distances, right, I'm smearing out that intensity to the point where at 15 microns of proximity, right, my square, the contrast is low. It's much wider than it was. It hardly looks like a square at all. And so contact printing and proximity printing are kind of two extremes. One is you're kind of looking for, you'd like to have both, both reduced diffraction and reduced defects. And so the third way is an attempt to do that, and that's called projection printing. So here you are not putting the mask and the resist in contact, and you're also not just putting a space in between them. Here you're putting actually quite a bit of space in between them, but in that space you are putting in optics to collect and refocus the light on the wafer. When you have an optical system, you're going to be diffraction limited. If you recall back, those of you who were in 680, we talked about the Rayleigh criterion and diffraction limitations when we were talking about optical microscopy, and why that drove the development of scanning electron microscopes, because you can decrease the wavelength, increase the resolution as you push out that diffraction limit at lower wavelengths. And so again, the use of this projection printing is another driver for decreasing the wavelength, because that wavelength also helps you with these optical systems as you project an image of the mask onto the wafer. And you can increase the resolution of these systems in the same way that you increase the resolution on an optical microscope. Right, so here we have the numeric aperture. This should look familiar. You have the index of refraction of the medium and the sine of the half angle. So bigger lenses give you a bigger half angle, right? Smaller distance between the projection lens and the wafer give you a bigger angle, right? That increases the numerical aperture and gives you better resolution. These systems also make it a little bit easier to make the mask because they are called, they can have stepping functions, right? So instead of, let's say you had a wafer and you, instead of imaging or exposing the whole surface at once, instead you just exposed, say, 1/4 of it. And you took the mask and focused it onto that 1/4, right? That would allow, optically, you can have a mask that is, 4 times the size of the wafer, which makes it easier to make your mask in the first place before you then use it to expose the surface of the wafer and create your pattern. You can also, right, so when we talked about in microscope optical microscopy, You can increase the half angle by moving the aperture closer, or the lens closer. You can also increase the refractive index, right? So we had immersion lenses. You also have immersion lithography, where you, instead of using air or a vacuum in that space, you could put in a liquid that has a greater index of refraction. Okay. And so the main trick to increase the resolution is to decrease the wavelength. But there are some advanced concepts that Campbell mentions that we can use to make improvements, further improvements, or additional. And many of them are focused on making improvements to the mask. So I mentioned in the previous slide here, or page, about projection printing and having the ability to expose a portion of the wafer and to magnify, or I guess it would be reduce the size of your mask optically. That makes mask making easier, right? If I'm going to reduce the size of the image of the mask by 4 times, right, then I can make the features on the mask 4 times bigger. And so this makes it easier to make the mask in the first place and to check that the mask is made properly. However, the more I step my projection system, the more I will reproduce a defect if it's present there, right? So let's say I have a defect on my mask. If I just expose the wafer 1 time, then I've created 1 defect. But if I step that 4 times, right, then that defect that was present on the mask is reproduced 4 times. And so I want to be extra diligent about finding and correcting any surface defects on my mask. Do this through inspection. So I can, if I find a defect, I can touch it up with an electron beam or a laser. I can also, during the exposure, insert what's called a pellicle. This is just a thin membrane at in between the projection and the wafer, right? So I have a membrane not at the focal distance, so it doesn't interfere optically, but it can catch, say, any particles and keep the surface clean. I can also deposit anti-reflection coatings if I'm worried about reflection, say at the resist interface, and I deposit a anti-reflection coating, then I can take care of that that interference due to the reflection. Another pretty nifty innovation is phase shifting. So normally we think about interference as being detrimental to reproducing our pattern. But in phase shifting, you actually take advantage of the interference to create a sharper line. So on the mask, if I add in additional material at a period that is twice my pattern, right, then I will get interference due to this additional phase shift material. And it will actually interfere deconstructively at the interface of the opening and right, of the transmissive and the opaque region, right? And that destructive interference actually creates a sharper line. So you need to make your mask in a complementary way to compensate for any distortion that will occur, right? So you can imagine how difficult this is because you have to accurately model the distortion, invert it, right, and then make your mask accordingly. In addition, so I mentioned the reflections at the surface, the interface between the photoresist and and the atmosphere, or the photoresist and silicon, as creating more interference. this can make it be made even more troublesome if my surface has peaks and valleys, right? Because as the light is coming in, I didn't grab the figure, but I guess I should have. It's in Callister. But you can imagine if I had a high spot, right, on the side of that high spot, I have a different angle. And so not only am I going to be reflecting, but I'm actually going to be reflecting at a different angle, not just straight back out, as if I had a flat layer. And so the more surface topography I have, the more complicated pattern of reflection that I'll have to deal with. And so this increases the importance of having an anti-reflection coating. It also can be dealt with by planarizing the layers. So being careful to, as you add layers to your device, to make sure that each layer is filled in and doesn't create a pronounced surface topography. Okay, so I'm pretty much out of time. The main idea here, right, is that we're talking about using light that's as small of a wavelength as possible to shine through a mask that has regions of opaque and transmissive material to reproduce the pattern on the surface, right? And this allows our device to have complex arrangements, geometries, and it's the one part of the microfabrication process that is not global, right? So everything else we are doing to the whole surface at the same time. And the only part of this whole process that encodes information is photolithography.